Hi, so in this video we're going to show how we can profile filters by setting up our signal generator to work with our oscilloscope so we can get views like this one. One of the ways that you can test the frequency characteristics of a filter or something like that is just to get your signal generator to sweep a range of frequencies, and you can do that with like the sweep menu, in this case for the FY6900, and you can put a starting frequency and an ending frequency and then push OK, and you'll see that it's varying the frequency through the range, and that's happening on the oscilloscope. The difficulty with that is you can't really look at the waveform at any point in time and know what the frequency is, and that's not so useful for profiling filters. So I'm going to show you a setup that will make it easier to sort of see what's going on with the filter. So the first thing that we're going to do is we're actually going to configure channel 2, and we're going to set its waveform type to be ramp, and we're also going to plug channel 2 into channel 2 of our oscilloscope. And turn on channel 2 here. So let's get going with that. And we'll make it so one of the things I'm going to do now, you can see channel 2's the waveform is switching across. So I'm going to change my triggering to be off channel 2. So I go to my trigger menu and I pick the channel 2 trigger, and that sort of stabilizes the ramp. I'm going to turn off channel 1 now just so we don't have that in the way annoying us. Now the next thing I'm going to do is, if you have 10 divisions between the start and the end of the ramp, then I know each division is going to be like 10% of the frequency range that we are sweeping. So I'm going to maneuver these to be 5 to the right of center and 5 to the left of center for this start and end point of the ramp. And I can do that in two ways. I can move the ramp left and right by adjusting the triggering point, and I can control the width of the ramp by adjusting its frequency. So what I'm looking for is, what I'm going to do here is just turn on my cursors so we can mark where we're trying to get things. And I'm going to put 1, 2, 3, 4, 5 divisions. So I want my ramp to start here, and 1, 2, 3, 4, 5 divisions, I want my ramp to finish here. So now if I vary my ramp frequency, that's too much, I need it a little bit less than that. Okay, that's getting close. Let's adjust our triggering point. Very close. Go down to a finer adjustment on the okay, and that's pretty close. I'm just going to wiggle my trigger point again. Right, so now my start and my finish are very close to 10 divisions across. Okay, so now I've got my triggering signal or the ramp all set up. What I'm going to do is start working with channel 1 here. I'm going to turn that on here as well. And we're going to pick a range of frequencies that we want to sweep. So let's say we want to do 0 to 20 megahertz. What I'm going to do is I'm going to set to channel 1, turn it on, adjust the frequency on the of the waveform to be, let's make it 10 megahertz. And then what I'm going to do is I'm going to go to the modulation menu, and I'm going to pick the modulation type of FM, and I'm going to make the range that it covers to be 20 megahertz, so it should go from 0 up to 20, which is double the frequency that I set it for sine wave, because it seems to sweep assuming that 10 megahertz is your midpoint. So here we go. I'm going to wind that back. I'm going to get to this point here, and we're going to take it up to 20 megahertz. Okay. Now what I've got going on is I've got a simple low pass filter with a resistor going through to a capacitor, and the capacitor goes to ground, and my measure point is at the corner between the resistor and the capacitor. And now we can see we've got the profile of our low pass filter, and I can kind of say that at the first division, that's going to be my let's say we're doing 20 megahertz, so halfway this would be at 10 megahertz behavior, so this is going to be like 2 megahertz behavior. And if I go and now change this filter around and make it like a high pass instead, so I'll just flip the orientation of these things. So now we've got our capacitor first, resistor second. We can see on the scope we've got a high pass filter where nothing at the start, and then very quickly we lose that attenuation, and then we can sort of let the signal through for the rest. So that's a quick sort of how we can set this up. I'm going to go back to the low pass scenario, so let's just flip these around again. Resistor capacitor. And there's our change in the waveform over the different frequency range. So then I can start doing things like seeing how it behaves with different capacitances, for example. So if I take my little block of different capacitors that I can switch between and put that in instead, I can then switch one of those on and get different behaviors depending on which cap that I switch. And also we can see with the breadboard, even when I take out all the caps, we can still see that we're getting attenuation because the breadboard already has some capacitance in it. Even though I don't have anything going from that resistor to ground, you can still see the attenuation. So now what we might do is we'll set ourselves up so if we can see if we can work out if we are hitting an expected cutoff frequency, which is where there's a 3 dB gain drop, or you could say the voltage amplitude is dropped to 70% of its maximum. So what we can do is if we get our signal and we get it so that it sits at 3 divisions up here, then 70%, it's not going to be perfect, but 70% is going to be close to, it's got little 15 little marks because it's 5 per division here. So let's say 15, and we times that by 0.7, like somewhere around about 2 divisions and a little bit, that's going to be the 70% drop. So what we could do is we can turn on our signal, and we want it to get it so that when it's unfiltered, that it reaches just fully up to this line here. So I'm going to vary the amplitude of that signal. I'm going to have to take it down because my function generator won't go higher, and I'm going to then make this bigger so we can drop this down. There we go. So that's pretty much bang on there. And then we'll turn on the modulation again. So now we can see that it's probably about here that we are down to about 70%, and that's about 2 divisions going out. So given we've got a 20 megahertz range, that's about 4 megahertz. Now the value of the resistor and the cap that we're using, the resistor here and this cap, so the resistor is a 220 ohm and the cap is 142 picofarad, and according to our calculator with 220 ohm and 142 picofarad, we're expecting around 5 megahertz. Looking at it on here, I sort of feel like it was closer to 4, but you get the idea, it's kind of within the ballpark. And if I go and swap out the resistor for a different one, this is a 1K resistor. Now we can see it drops off a lot sooner, so maybe half a division there, so perhaps 1 megahertz. And if we go to our calculator and we go with 1000 ohms there, the expected value is about 1.1 megahertz. So we kind of are seeing in the basically we're seeing in the experimental evidence on the oscilloscope that the predictions according to the physics equations are kind of working, which means that I think that the setup that we've got here for doing these sort of filter measurements basically works. And we're also not limited just to deal with RC filters. We can use this for any purpose. So in this case I've got an inductor and a capacitor in series making a bandpass filter, and we can see the profile of the bandpass filter working there. Okay, so thanks very much for watching. Hopefully this was interesting for you. See you next time.